Welcome to the session Exploring New Storage Paradigms and Opportunities with Persistent Memory Technology. My name is Daniel Waddington and I work for IBM Research Almaden. I'm going to break the presentation down into three parts. First, we'll look at the technology and examine what it really brings to the table. Then, given this in mind, we'll look at rethinking storage. And specifically, I'll introduce the IBM Research prototype MemoryCentric Active Storage, also known as MCAS. This will follow with some future directions. To remind everybody what Intel Octane DC persistent memory modules are, let's look at this slide. This technology is the first storage class memory that's designed for enterprise storage domain. And it's based on 3D Crosspoint, which is a lattice-arranged phase-change memory. It comes in the form of modules that sit alongside the DRAM modules, and these capacities are 128, 256 and 512 gigabytes. So this gives you approximately 8 times the capacity of DRAM at approximately half the cost per gigabyte. Let's look at some of the key positive attributes of this technology. First, it's load store accessible. That means that the CPU can actually issue instructions to retrieve the data directly. For example, a 64-byte read or write will take in the region of 300 nanoseconds access latency because the transfer is coming across the memory bus as opposed to the PCI Express bus. This gives us the potential for a synchronous access model, which ultimately helps us to simplify the software design. The technology also has a minimal media controller. Unlike NAND flash, there is little queuing and no garbage collection going on. So this means that the latency and the high throughput dimensions can be achieved effectively queue depth 1. This is something that you don't typically see on an NVMe device, which its latency and throughput are at different ends of the spectrum. This minimalization of the controller also allows us to maintain the synchronous access model. As I mentioned previously, this helps to simplify software design. The technology also allows smaller read-write amplification. So on the CPU side, this is 64 bytes, a cache line. Internally, this is 256 bytes. This finer-grained access does allow high performance for sparse data accesses. And it also helps you to simplify data structures again, and avoid technologies such as log-structured merge data structures that effectively take a random workload and serialize it to make it more friendly to the storage device. The performance is also more predictable, and this importantly shortens the long tail latency. So now let's take a look at some of the negative attributes. Firstly, performance is asymmetric. That is, the read performance is generally higher than write, and sequential is generally higher than random. Furthermore, writes do not scale well with threads. You can see the graphs here. On the left we have throughput, on the right we have latency. Looking more closely at the throughput, you can see that for the read workload, performance scales almost linearly with the number of threads. However, for the write workload, the blue line, you can see that the performance thresholds at about 1.5 gigabytes per second. So clearly the writes are not scaling. The uptick in the write performance faster than read, we believe, is due to internal DRAM buffering on the device. That happens before the 15 thread count. Also, this technology can be consumed as a block device. However, the research that we've seen indicates that in order to do so, you really need to use a persistent memory-aware file system, such as Nova from UCSD. Putting an existing file system like XFS or ext4 will not result in good performance. Power fail consistency is also very fine-grained with this technology. It's only 64 bits aligned. This means that the onus of software is considerable in managing crash consistency. And this usually means that the complex software around this results in performance loss. Furthermore, good performance relies on striping data across multiple DIMMs, typically 6 DIMMs in a single socket. The DIMMs may be configured as individual elements, but performance is significantly reduced. The DIMM striping model is also very simple. There is no inter-DIMM erasure coding, for example. This means that RAS and field serviceability is strained. In the event of a DIMM failure, the complete region is essentially lost. Let's look at where this technology really excels. It excels with small, unpredictable access patterns. Here, where low latency to read and modify data and make it accessible to the CPU is important. So here, note the word unpredictable. You can't do prefetching on the data. So if you can't do prefetching, latency is more important. If the workload has more reads than writes, then this technology clearly does better. It also does well where rebuild and recovery costs can be reduced using locally durable and consistent data. So for example, if you have a network node which has a relatively slow network link and therefore can't rebuild from peers across the network, then using locally consistent data can help. In terms of capacity, the sweet spot is essentially between 1.5 and 6 terabytes, depending on the size of DIMM that you choose. We do expect that to increase with future revisions of the Octane technology. Now we're going to look at IBM's MemoryCentric Active Storage, MCAS. This is an IBM Research project that started in approximately 2018. It's an open source project and is available on GitHub. The focus on the project is to build a new type of storage system with the explicit goal of leveraging new persistent memory technology. Of course, we built this around the Intel Octane DC persistent memory DIMMs that are available in the marketplace. The storage system has a number of common or familiar elements. However, it does also bring together new elements that aren't so familiar. Of course, it's based on persistent memory and crash-consistent data structures, and it leverages the idea of in-store operations, or what we term as active data objects. Finally, it's made extensible with a view to adding acceleration and supporting ultimately disaggregated memory and related technologies. So what are the founding tenets for MCAS? The underlying design is a key value paradigm, essentially with extensions for in-store compute. Everything is synchronous, and the operations are immediately consistent. So for example, when a put command returns, all data has been made fully persistent. The storage is network attached, so the data resources can be shared among multiple nodes in the network. However, it is aimed at fast networks in the data center, and this is so that we can maintain an immediate consistency whenever possible. But I should note that MCAS does allow basic support for basic TCP/IP sockets, so not having RDMA isn't a showstopper. MCAS also allows arbitrary sandboxed in-store operations. This basically means any code can be deployed into the storage system where it can act upon data. It allows flexibility in implementing crash consistency because, of course, the data structures in the persistent memory need to be crash consistent so that they can be recovered in the event of power failure. This can typically be done by hand with software transactions, hardware transactions, or compiler language extensions. Finally, MCAS avoids using memcopy for large transfers of data and uses direct DMA, and in fact does support things such as GPU direct technology that allows you to move data from the storage system directly into the GPU card, bypassing the host CPU and DRAM memory. I like this little quote from Andrew Tannenbaum's Distributed System book. Basically says, immediate consistency and a simple consistency model really make it more friendly for application developers. If the consistency model is too complex, developers really have a hard time building correct applications. So this is one of the reasons that we've tried to maintain a very simple consistency model. Let's look at the base performance for the MCAS Key Value Store. This is actually published recently in a paper in ATM IEEE ISPAS, so you can look up the details in your own time. This data is without in-store operations, so this is the basic key value operation of the system. In summary, you can see for a single socket, of course this being an Intel Cascade Lake processor, for random read key size 8 bytes, value size 16, we observe approximately 10 million IOPS. For random write key size 8, value size 16, we see approximately 6 million IOPS. Also note that the latency round trip time for a put is approximately 7 microseconds, and that's across 2 network hops and a single 100 gigabit Ethernet switch. MCAS is based on a sharding architecture. Each network node can manage one or more virtual machines or containers, or of course use bare metal. Each process maintains a shard and a network endpoint. Shards manage multiple pools, which define a collection of memory resources, or regions, and also define the memory and CPU resources for the in-store compute. Each pool has one or more keys, and each key has one or more values. Note here that the protection and visibility boundary for in-store operations is actually the pool. We'll talk a little bit more about this later. MCAS provides an open protocol architecture. So this allows you to layer services on and provide in-store compute, sometimes known as pushdown. And for our system, we call those active data objects. The basic reasoning for this is to essentially reduce data movement across the network by pushing compute to the data, as opposed to vice versa. The ADO mechanism allows you to implement arbitrary protocols and arbitrary functionality. What ties the two together are an ADO adapter on the client side, the protocol definition, and the interpretation of the protocol in the ADO plugin on the server side. So you can imagine there are many things that you can do with the ADO layering, and incidentally, multiple ADO plugins and multiple ADO layers can be put together. There are effectively 2 types of ADO layer, generic and domain specific. So for instance, for generic you have things like replication, compression, encryption, erasure coding, etc. Those are layers that apply functionality that is useful for any application. And those are typically what we see in, for instance, NVMe SSD devices today. Then there are domain-specific ADO layers. These are tied directly to the application. These may be data manipulation, conversion, summarization, data derivation, or specific domain operations such as matrix multiply. The MCAS architecture is primarily software defined. It supports a flexible deployment model on bare metal, virtual machines, or containers. The primary API is C++, however we do support Python as a secondary language. And the APIs are on the client side as well as the ADO plugin side. A deployment typically consists of a shard process together with one or more ADO processes. The shard process maintains a number of shards. Each shard is managed by a single shared nothing thread that manages a network connection endpoint, a key value engine, i.e. a hash table, an optional key value index, e.g. a red black tree, and a set of memory pools. A memory pool basically defines a set of memory resources, particularly persistent memory resources. The memory pool memory is shared with the ADO process via the kernel, and therefore the ADO process has complete visibility of the memory pool in its own address space. However, the shard process and the ADO process do communicate through user level IPC. This ensures fast communication. The plugin has, as I mentioned, complete visibility of the memory for the memory pool. That memory may be a single contiguous or multiple contiguous regions if memory pool expansion has occurred. The plugin is basically a C++ library that conforms to a specific interface, the ADO interface, that gets upcalled as messages are passed from the client through the shard process into the ADO process. The custom ADO plugin is the only one that really knows how to interpret a message that was compiled and assembled on the client side by the ADO adapter. The ADO plugin also has the ability to create new key value pairs, to look up key value pairs, to allocate and free memory from the pool, and also to do some checks on how much pool is available and so forth. But basically the ADO plugin is flexible to do whatever it wants with the memory. And so for instance, a typical deployment will be that key value pair has a value root, which is the root pointer to a data structure. Then this data structure can be amended or appended to with pointers and additional allocations of memory. Note that in typical ADO process deployment, an ADO plugin deployment, a localized heap allocator is used in the ADO plugin. So that means, for instance, a coarser-grained amount of memory is allocated through the callback to the shard process, but then that coarser level of memory is managed locally in the ADO process by a custom heap manager. ADO plugins are primarily written in C++. Each plugin is a dynamic library that conforms to a predefined C++ API. However, it is possible to embed other languages inside that component library. We currently only support device DACs, and the reason we do this is initially to ensure crash consistency and persistency in the advent of RDMA transfers to the memory. However, we do expect to support FSDAC soon, which will make the assumption that on-demand paging hardware is available. Crash consistency today is achieved by the handcrafting or using software transactions in the form of instrumented STL containers. We've taken the EA Games STL implementation and instrumented it so that you can use it and have transparent undo logging, which is available at the method level interface. We also hope to explore future work in the areas of language compiler-based approaches and hardware support for transparent undo logging. So as I've shown you MCAS, you probably get a feeling of the features that it has and the capabilities. And you can see that the ADO mechanism basically allows rich services to be layered on top of the conventional key value store, using persistent memory at the heart. Here are some examples of things that we believe are good use cases for this technology. So in storage systems, using the MCAS to manage durable metadata and indexes and so forth. Data curation, doing EDI transforms, compression, decompression, sorting or filtering. Real-time data analytics, where latency is important. We can implement domain-specific data structures such as KD trees, etc. And then finally, real-time cognitive applications and knowledge processing applications that use things like graph processing, inferencing, or sparse distributed memory. So there are many different applications that really are suited to MCAS. Okay, now to give a better understanding of the active data object mechanism, I'd like to go through a small example and some code. So this example's actually in the MCAS repository under examples personalities, example_fb/source. FB is for flat buffers because we're going to use flat buffers as the mechanism for the protocol. What we're going to do in this example is basically construct an ADO that will allow multiple versions of a key value pair to be held in the system so that you can revert to a prior version of the key. So of course we have put and get operations here, as well as a message for getting responses from those operations. So the first thing we need to do is to ensure that the appropriate kernel module is loaded. Here we have MCAS mod, and that's used for the persistent memory backend called HStore. So you need to ensure that this is loaded. You also need to ensure that you have persistent memory available. course this has to be configured as device DAX memory, and it has to have the appropriate permissions. Here we've just given full permissions. Okay. Now if we look at the source code is broken down into the client side and the server side plugin. So let's take a look at the client side. The client side is going to provide the normal operations, creating pools, opening pools, closing pools, etc. And of course the put and get operations. If we look at the implementation of the client side, we can see that what we're actually doing is packaging up a message, creating a flat buffer's message for the given request. So let's have a look at put and get. So for the put operation, we actually create a message using the flat buffers library. And then what we do is we use this special call called MCAS invoke put ADO, which basically takes that message and transmits it across the network to the server. And it's this message that's passed opaquely through the shard process to the ADO plugin. Likewise for the get, we also create a message and then forward through the invoke ADO. So you can think of the invoke ADO and invoke put ADO as special enhancements to the conventional key value API. In fact, if we have a look at the API for the MCAS core capability, if we go source component API MCAS ITF, this gives the basic interface, and you'll see in here we have things that you would recognize such as put and get, and we also have things like create pool, open pool. But then in here we have this invoke ADO and invoke put ADO. The difference between the invoke ADO and invoke put ADO is that put implicitly carries a value to be put into the key value store before the ADO plugin is actually invoked. Okay, so if we go back to the code, you can see that the invoke ADO is also targeting a specific pool and key pair, and it's carrying the flat buffer message as well as some value data that's going to get implicitly put into the system. If we now look at the server side of the code, the crux of it is the ADO plugin. So the plugin implements a particular interface. In fact, let's open that interface, ADO ITF, and in here this defines crucially the do work operation. Do work is what is upcalled by the ADO process when it receives a message from the shard process via the user level IPC. Okay, let's take a closer look at the do work operation. The do work is what's upcalled by the ADO process into the plugin, and it carries information about the key being targeted, various values that are being potentially passed, and the in-work request, which is essentially the message from the client side. And it's up to the do work operation to handle the different messages that come into the system. So for instance here we can see we have a put handler as well as a get handler. If we look closely at the put handler, it basically unpacks the message and then calls a operation on the root data structure, and the operation here is add version. If we take a closer look at add version, you'll see that the add version operation has to be crash consistent. So here we're using basic undo logging to make sure that we have that consistency. So for instance here we create the undo structure, put in the prior values, perform the transaction, then clear the undo log. Here you'll notice we're using the pmem library APIs, e.g. pmem persist. When the system comes up, we check for recovery, and here we're using the fact that the timestamp is not 0 indicates that we're in a mid-transaction. Otherwise the undo log is actually cleared. So we have to check for this recovery and the execution of the undo. So actually building this code to be crash consistent can be tricky. This is handcrafted code, as you can see, but there are frameworks such as PMDK that will likely make that easier. We also have ESTL implementation, an STL C++ implementation that supports undo logging transparently, so you can use familiar data structures instead of having to rewrite your code. Anyway, let's go back to the ADO plugin itself. So you can see that we call the add version operation, then we create a response buffer back for the client and send that back to the client. Likewise for the get, we unpack the message, we call an operation called get version, and we put the result in the flat buffer response, and we push that into the response buffer vector, which gets sent back to the client. So it's as easy as that. So the code in here for the do work could literally be anything that you really want, depending on the application and depending on the data structure. For us, we're doing versioning in this particular example. So that means that we make sure we have multiple versions of the key value pairs. In fact, I think we have 3 versions, and then we can rewind those versions and request prior versions from the client. Okay, now I'm going to run the code. First thing I'm going to do is ensure that it's all built. Then I'm going to run the MCAS server, which should be in the dist binary directory. And I'm going to provide it a configuration file. Actually, let's quickly take a look at the configuration file. The configuration file defines the shard and a number of attributes on the shard, such as the core, the port, network, etc. Here you'll notice that the backend we're using is HStore, which corresponds to the persistent memory with the hash table. Of course, it's crash consistent. We also outlined here or identify the ADO plugins. So here we have this lib example FP, which is the dynamic library that's loaded by the ADO process, and it's this library that will ultimately provide the do work operation. So it's important that we have a configuration file because we need to pass that to the MCAS command line. I'm also going to put a debug option on of 1 so we get some debugging. Now I'm going to open up another window that we're going to use for the client. The client's called personality example FB test. I'm going to now run that, and you will see it connecting to the MCAS server and performing some operations. Before we do that, let's look at the operations we're going to perform. Basically, we're going to do a set of puts, and then particularly for a chicken, we're going to do multiple puts of the key chicken, starting with Nugget, then Bob, Rosemary, and so forth. And then we're going to show that we can retrieve those different versions back using the get operation. So these puts and gets are actually calling on the client interface, which does the wrapping up into the flat buffers protocol, etc. Okay, so let's give it a try. Just takes a little while to get the handshake done on the network, but there we're done. Okay, you can see here that we've basically done renaming of Bob, a chicken from Bob to Rosemary to Verde and to Zucchini, and we're able to actually recover the current version Zucchini and the prior 2 versions Verde and Rosemary. So you can see that it's relatively easy to get going. You run the shard process and then you run the client itself. The shard process, of course, will instantiate another process called the ADO process. I'd like to just quickly finish by showing you how to debug that. One way you can do it is put a command line here called use extern, and I'm going to put use GDB, which basically means the ADO process will be launched in a separate extern and within GDB. So let's do that now. You can see it creates a new window down here. It's a little bit small, so I'll just make it a little bit larger. And this is the execution from the actual ADO plugin. So you can actually break and put breakpoints and so forth into this, and it helps you to debug it. But it's important to remember that the ADO plugin is ADO process, is a separate process from the shard process. It's actually a child. What's really important to note here is that we implemented this versioning scheme as an ADO plugin. So the base MCAS capability doesn't provide versioning of key value pairs. However, what we've managed to do is essentially layer on top of that an ADO object which provides a versioning service. So whatever functionality you want to introduce into the key value store, the ADO plugin allows you to do that. We'll now explore some of the future directions for persistent memory technology. The first I'd like to talk about is opening up the memory bus. IBM has been offering this capability through OpenCAPI for a number of years now, but we're seeing standardization such as Compute Express Link coming closer to reality. What this does is allow cache coherent attached memory and accelerators. This will ultimately drive broader multi-vendor adoption of persistent memory, enable CPU memory disaggregation for flexibility, and also allow custom intelligence to be pushed closer to the memory. So opening up the memory bus is a first important step, and as we see these standards come into fruition, we'll see more capabilities come to the marketplace. IBM Power 10 already provides these types of capabilities through the OpenCAPI, Power Axon, and Open Memory interface. This allows us to attach specialized or storage class memories or specialized DRAM into the system and make it load store addressable from the processor. Furthermore, we can do clustering. So for instance, we can build a cluster of nodes where each node through hardware has access to other nodes' memories. So what we used to do in software, we're now able to start doing in hardware. The system is also designed to take high-performance devices such as PCI Express 5. We're also entering an era where the scaling of capacity is outpacing the scaling of compute and network. So this is what I like to term as dark data. We may end up with a point where there's so much data in the memory, in persistent memory particularly, that we can't get to that data because the compute hasn't scaled accordingly. So what we really need to do is to minimize data movement. And we need to look into technologies that push processing closer to the memory, processing in memory. You can differentiate these as two types: processing near memory, such as UPMEN, which effectively puts small cores or microprocessors close to the memory cells or close to the memory banks, and then processing using memory, where resistive memories are used directly to do computation. There are academic examples today of using processing using memory around graph processing, pointer chasing, genomics, hyperdimensional computing, and so forth. So although this technology is quite a way off the marketplace, I do believe that this is a direction that we will have to go in order to scale the compute as we are increasing the scalability of the capacity of memory. Programming languages are also another thing of importance. Making crash-consistent data structures and operations easier for the developer is going to be fundamental to the success of this technology. Today we sort of have to craft things by hand, rewrite software according to frameworks and so forth. Ultimately, what we want to be able to do is allow developers to use legacy and familiar data structures and eliminate the need for data structure serialization. This is realizing the memory storage convergence paradigm. We need to move to new languages and new compiler technologies which will take some of the onus away of making software crash consistent and dealing with the hazards of doing so. Then from the install or push down compute perspective, we need to start looking at some existing sandboxing technologies and how these can be used to maintain integrity in in-place modifications. So there are techniques such as Rust and Splinter type approach, and also WASM, that are two technologies that could potentially do sandboxing in the context of in-storage compute. Then finally, we may start to move towards more hardware support for crash consistency. For instance, using hardware to do transparent undo redo logging in the memory controller. Something that we're exploring in the context of OpenCAPI at IBM. From the perspective of in-store compute, obviously sandboxing technologies are becoming more important. Technologies such as Rust, which does compiler time verification, and WebAssembly might be two options to help us with this problem. We also need to look into cooperation with additional hardware support. For instance, use of hardware to do transparent undo redo logging in the memory controller. This is something we're exploring in the context of OpenCAPI at IBM. So to summarise, potential of persistent memory technology is starting to be unlocked. We've still got a long way to go, particularly from the software side and particularly in realizing the benefits. Of course, there are other hardware modifications that could be made to make life easier for the software. These will likely come down the pipeline. And persistent memory isn't the silver bullet. It's not good at everything. It's good at handling certain types of data. IBM's MemoryCentric Active Storage takes a new look at storage design with persistent memory in mind, taking traditional key value paradigm and extending with persistent memory and in-store compute. This basically allows us to reduce the amount of data that's being pushed around the network and just push the compute into the storage system itself. There are also emerging interconnect technologies such as OpenCAPI and CXL that will likely increase opportunity and volume of persistent memory adoption. And then for the long haul, to address the the compute scaling limitations as capacity scaling continues, we're going to start needing to look to things like processing in memory concepts that will help us to do that. MCAS is available as an open source project, Apache 2 licensed on github.com/IBM/MCAS. Please bear in mind that this is an early prototype, but it is functional. And of course, we welcome new use cases and contributions, and we hope to keep developing this technology. Thank you for your time, and please take a moment to rate this session.